Hi everyone, and welcome to my talk. First, I would like to thank you for staying all the way until this very last talk of today. My name is Dragana. I'm a PhD student here at EPFL. And today I will tell you a bit about what I do with Scala, which is a bit of teaching and a bit of formal verification. So the story starts with this pretty picture that some of you might have seen a few days ago. So it's not just a random picture from the internet. It's a picture taken by Daria a few weeks ago here at EPFL. And so it's actually a first week of the semester. It's a functional programming class taught by Martin that you can see at the start of this room. And as you can see, we have more and more students taking this class. So this year, all the stairs are full on top of all the chairs and everything. And so I would like to also show you this other picture, which is also not a random picture taken from the internet. I actually took this picture a few years ago, and I think it nicely shows you what happens behind the scenes in this story. And so the picture was taken at the University of Belgrade, where I used to teach several courses. And here you can see my colleague, Milana. And in the background, you see a pile of exams that we would grade over the course of the semester. And yeah, this picture is just here to remind you how much work there is to run those courses. I don't know exactly how many copies there are in the picture. It was a while ago, but I can give you some numbers for this year for EPFL, for functional programming. So this year, we had more than 400 students, or we have more than 400 students taking the Scala class. And as you can see, the number is growing over the years. And so this number, what you should have in mind is that those students are taking exams. So there is a midterm exam, there is a final exam. On top of all this, or in addition, throughout the semester, they are also solving a bunch of exercises. They are solving labs that are also graded. And so all of those exercises and all of those labs contain multiple smaller exercises within them. So when you multiply all of this, you get to a pretty large number. And to also get you some idea of what's inside of those notebooks with those exams, I have this example exercise for you. So you can maybe take some time to try to solve it. It's an exercise that we give students already in the first exercise session. So it's asking you to implement exponentiation, but fast exponentiation. So it should be running in logarithmic number of steps. So I can also give you a small hint, which is what we give to our students as well. So it's a formula, it's a recursive formula that tells you how to compute this. So it basically tells you if the exponent is even, you do what you would normally do. You just multiply one step at a time. And if it's odd, and if it's even, then there is this fancy formula that allows you to do this a bit faster. So I'm not sure if you have much time. I'm sure some of you already solved it, right? So I can already show one solution. And now I would like you to take some time to look at this solution and to grade it. So to tell me if this solution is correct or not. All right, and now try to imagine doing this. I said 400 students, so try to imagine doing this 400 times for 400 similar pieces of code. This takes time, right? So in this talk, I will try to tell you a bit about our automated approach for this. So this picture kind of summarizes the talk. On one side, we have a bunch of solutions, so those 400 submissions. And we also have a correct solution written by the teacher. So what you wrote just now at the start. And then on the other side, we have some classification. So the idea is that all the solutions that are equivalent to these reference solutions are considered as correct. And those that are not, they are considered as incorrect. So I can show you a bit of how this works. Let me just see if this works. No. Okay. So here I have a very tiny demo that I would like to run just to give you some sense of how this works in practice. So I prepared here several files with several various implementations of this exercise. And now I will run the tool, which is going to automatically go through these examples, compare them to my reference solutions, and tell me they're correct or not. So here you can see the command, but basically I'm just giving paths to those files, and I'm saying name of the function that I'm checking. So it's always called the fast exponent, exp, in all those files. And I'm giving a name of my reference solution. And okay, some other parameters like timeout and nothing very important. And then the tool will run on those. It will print some logs in the process. And finally, in a few seconds, we will get results, which are basically this classification that I mentioned. So we should know, in maybe 2 seconds, we should know which of those candidate solutions are correct, as in equivalent to my reference solution, and which of those are incorrect. Okay, so here we get some logs, and I can pause to explain what we see here. Oops. So what I see is a list of solutions that are correct, so that are equivalent to my reference solution. So you see that this is almost all the solutions here. Then I have on a list of errorness functions, I have this one solution. And I also have a third category, which is timed out functions. Those are the ones where we couldn't, in this timeout, we couldn't neither prove equivalence nor disprove it. So we don't know if the solution is correct or not. And if I continue, you can see that for here on the very bottom, that for this one solution that's not correct, we also get a counterexample. So we know the input for which this solution doesn't work, which is super useful for students to know how to fix it. So now, if I manage to go back to my slides. Okay. Now we are back in the slides, and yeah, I started by showing you some pretty pictures, and then I'm talking about proofs. So you might want to stop me here, right, to ask some questions. And the first question would be, why are we suddenly talking about proofs? So why do we care about proofs suddenly out of nowhere? And I'll try to explain the reasons. So the main reason is because testing, which is the obvious alternative to this automated approach, is not good enough. And why is it not good enough? So first, for automated testing, you need a bit more work than what I'm showing here. You need to write those tests, right? And then it's not that you only need more work, it's also that this work might not be good enough. So you might miss some tests that are very important, and you might say that some solutions that are incorrect are actually correct because you don't have good tests. So I have one example here, which makes it very hard to come up with good tests, or even impossible. So it's an exercise that asks students to implement addition of natural numbers, where natural numbers are this user-defined class. Okay. And so there is a group of students who solved it in a way similar to what you see in this slide. So instead of adding those user-defined natural numbers, they are converting them to integers and then back. And so the problem is that natural numbers that we want are infinite, and integers in Scala are limited, right? So what happens here, what could happen for some large numbers, are overflows, and this kind of destroys the result. And the problem that we have here with testing is that such numbers are so large that we cannot possibly construct this counterexample, right, with this hardware. And so without this counterexample, we can wrongly claim that this solution is correct, which is terrible. We really don't want this. So that's why we care about proofs. You might also be wondering, if we care about proofs, why do we care about equivalence checking in particular? Because there are many other kinds of proofs. And the reason is also very simple, is because proofs are very hard. Formal verification is very hard. So it's my job, and it's very hard for me. It's not a job of teachers and students in introductory classes, so it's even harder for them, right? To show you this, I have this example from our benchmarks, which is part of the implementation of red-black trees. So it's just one of the operations. And here in this lower part with this ensuring, you have a specification. So we have a definition of what this operation should actually do in order to formally verify it. And you can see that it is a bunch of code, and this code is really hard to come up with, and it's also really hard to prove. Sometimes you need to write additional lemmas and stuff like this, and we don't want to worry about this. What we do have to worry about is writing reference solutions, and so this is why our approach naturally makes use of this. So you only have to provide this reference solution, and then we rely on equivalence checking to prove that candidate solutions are correct. Now, on this picture, you see some more details than what I showed before. So on one side, we still have all the programs. On the other side, we have this classification. And now you kind of are starting to see what's happening in the middle. So there's this magic box in the middle that we call stainless that does all kinds of stuff. So it starts from Scala programs, then it translates them into abstract syntax trees, then it transforms those trees a bunch all the way up to some formulas, and then it talks to SMT solvers to check if those formulas are correct or not. We will basically, the equivalence checking approach that I'm talking about now will be built upon this box, will be built upon stainless. So I would like to spend at least this one slide telling you about the base, telling you about stainless. So it's a verifier for Scala. If you don't already know about it, here is a link to the EPFL, stainless.epfl website, where you can actually get the tool, you can see the code, you can see a bunch of examples. We used stainless, and other people use stainless a bunch to prove many Scala programs. And I listed here some interesting examples. So we used it for a bunch of algorithms and various data structures. I showed you the tree already, but also for more serious algorithms such as some blockchain clients and cooperation algorithms. So also on GitHub, you can see all those examples, and you can also play with them a bit. And I put here a bunch of other resources that you might want to look at. All right, so now that we are familiar with stainless, I can tell you about equivalence checking. So the talk will be about those three pieces that kind of build upon each other. And I will explain this approach bottom up. So first, I will tell you about the very basic piece, which is this pairwise equivalence checking. So what this means is looking at two programs, looking at two functions, and deciding whether they are equivalent or not. Once we know that, we can move to the middle layer, which is looking at programs that contain multiple functions. So we know how to deal with functions. Now you have to see how programs call those functions, detect pieces that might be equivalent, and rely on what we already did to reason about programs. Once we know that, we can go on to the top layer, which is this clustering algorithm. So now that we know how to reason about programs that consist of multiple functions, it's time to see how to reason about multiple programs. So you saw before there are 400 programs, right? So we need some efficient algorithm that can look at all of them and classify them. So let's start by this first piece, which was pairwise equivalence checking. So before I tell you how we do this, I should probably define it, because equivalence of functions is defined in various ways depending on who you ask. So for me, I will say that programs are equivalent if they have the same signature, if they both terminate, and if for all inputs they return the same output. So you can see here that we are not talking about side effects, we are not talking about prints or anything like this. So programs are just pure functions, and we are just looking at this input-output correspondence. All right, so now that we agree on this, I can tell you how we automatically prove equivalence of functions. So I will do this through this example. It's an example program that checks whether a list is sorted. So it's a very introductory example. You have as input, you have a list of integer, and then as output, you have a Boolean that says true if the list is sorted in an increasing order, I would say, and false otherwise. And so you have here, I have two programs. One is, let's say, a student solution. The other one is a reference solution that is, of course, correct. And now I want to check if they're the same. So the way to check this, using formal verification, using stainless, is to write this lemma and to ask stainless to check whether this is true or not. So the lemma only says what is here in this ensuring, which is prove me that this function is sorted f returns same stuff as is sorted m for all input lists f. And if you ask this to stainless, it will get very busy, but it will not tell you the answer because this is too hard. Those two programs are recursive, and proving equivalence of recursive programs is very hard. So instead, you will need to help it a bit. So you will need to provide a proof. Okay, and so here I also show you this proof. And the way we prove equivalence of recursive programs is by using induction. And induction on a body of a function. So it's called functional induction. One thing that I have to tell you at the very start is that all this code that you see now is automatically generated. So all those transformations that are in this magic box, this is what they do. Okay, none of this is written by users. No, users or teachers or students, they don't have to worry about any of this. And so the lemma and the proof are all automatically constructed. And now that you know that, I can tell you why is this a proof or how is this a proof. So if I zoom in a bit on this proof, you can see that it is exactly the same as the function that I showed you at the very first slide. So is sorted f. It's exactly the same as this. It's just it has a different name. It's called int proof, okay, because now it's a proof. And in addition to its implementation, it has this ensuring attached. And why is this a proof, and particularly proof by induction? Well, because if you look at this empty space that's going to transform now, so if you look at this recursive call to the function that we had, and if you unfold it a bit, so if you replace it by the function's body, what you get here is a bunch of code that is exactly the same, right? I just unfolded the function, all of this is the same. And as a bonus, you get this assume. So what this means is that once I unfold the function, if it had some ensuring, if there was something that I wanted to prove about it, this means that once I call this function, I can assume that after I call it, this holds. And now you might already be able to see that this is actually a proof by induction, because this very combination of these very two last pieces of code, of assume and ensuring, is kind of like an inductive step. So I assume that this holds for T, which is L.tail, and then I can prove that it holds for L, which is the entire list. And the reason why this works is obviously because we have this base case, right? So this doesn't go on indefinitely. At some point, I will end up here, and once I prove this, then stuff unrolls. Right. So we have our proof. It's let's say it's a happy ending of this first part of the story. We can go on to the next piece, which was a function called matching. So I said programs usually consist of multiple functions. And so now we are looking at this problem of matching those functions. So the problem I will present using those few pictures. So let's look at the first piece of this graph. So those two programs. The first one is a reference solution M. The other one is a student solution F. So let's say that those two dark blue nodes of this call graph are equivalent functions. And so what we do is, if we manage to prove equivalence of functions, then we can replace calls to equivalent functions. So instead of calling this one, if it's equivalent to this one, I can basically merge those nodes. I can call the same one. And so this I can do as many times as I want. Now, if I manage to prove that this light blue node is equivalent to this light blue node, I can also merge them. I can just call this one because they're both the same. Okay, and I do this all the way until I reach the top level. To show you this on an actual example, I have this other code, which is a solution to an exercise that asks students to implement a distinct method on lists. So basically just to remove duplicates. If you have list 1, 2, 2, 3, 3, 4, it should be 1, 2, 3, 4. You remove all the duplicates. And so the way this is done here in this student solution, there are three functions. So there's this main function that calls this tail recursive function. So this one here has L1, it's going to be some accumulator. It has L2, which is our original list. And then it iterates on L2, and if it finds a new element, it adds it to L1. If it already belongs in L1, then it doesn't. And it calls this function is in F to check whether something belongs to a list or not. So here you see there are three functions. So if I just try to directly prove equivalence of this program and some other program, this is very hard. Instead, we look at those three pieces and we try to prove them one by one, like I showed in the previous picture. One thing that I didn't say in the previous picture is how do we know which nodes might be equivalent? And this is actually a very hard problem. We have two ways or two approaches to this. So here's what we do. If you look at this second part here, so those are the three definitions that I showed you before. It's just declarations of those three functions. And then here's a reference solution. Again, it's just declarations because otherwise it takes too much space. But anyway, we're looking at the problem of how to know which function from the reference solution might be equivalent to this one, to this one, to this one. The way we do this is first using something called type-directed search. So basically what we do is we inspect signatures. And here we are very lucky. There are those two functions is in that both have one integer and one list. So it's very easy to assume that they might be equivalent and to try to match them. Once we prove equivalence, to merge them like I should, and go Sometimes this is not as easy. There could be examples where there are multiple possible candidates where types match, and then it's not very clear what to do. So for example, here, unique F and unique M, assumingly this is the only way that we can match them, right? There is this one pair, but there are actually two ways. One way would be to say that unique F of L1, L2 is the same as unique M of L2, L1, and the other would be to keep the argument order. So in case that there are multiple possible alignments, what we do is something called test-directed search. So what we do is we run those two functions on a few test cases, and then if they fail, if they don't provide the same output on some test cases, then we know that they're not a good match. And only if they pass all the tests, we take them as a good match. And so if you remember at the very start, I was trying to tell you that testing is not good enough, and I still mean it. Here we use testing not as an only way, but just as a way to speed stuff up, because verification is very slow, takes so much time. So we don't want to try all the combinations using verification. So instead, we use testing to quickly identify what could be equivalent, and only then we prove those good candidates. All right, and now to put this all together, this is the student code after all the transformations. So once we decide that this is in F is the same as is in M, we can just replace it. So we can cross out the old call and we can replace it with a new one. And then once we do this, it's going to be very easy to also prove equivalence of unique F and unique M. And so then in the main function, we can also do this replacement. Here you can notice in this last replacement that the order of arguments changed, right? Because it turns out here the student did the matching on L2 and used L1 as an accumulator, while the reference solution did this in the other order. But using this test-directed search, we could quickly detect this and align those arguments. All right, we reached the second happy ending of the day, so it's time for the third piece and for the third part. So it's about this final algorithm that takes as input a bunch of candidate solutions and then classifies them using what I showed you so far. To explain this a bit more, I would like to zoom in on this picture that I keep showing you on this result side of the picture. So here what you see is a graph from that you obtained as an actual result by checking for equivalence of around 170 programs that implement a function that finds the maximum element of a list. So I was actually surprised by looking at those examples at how many different ways there are to find the maximum element of a list. And so what this graph shows you is in the very center is our reference solution. So we only have one reference solution. And all those other dots, those are student solutions. And the line means that our clustering algorithm managed to find the connection. And so it means that we managed to prove the equivalence of those two dots, of those two programs. And what's interesting with this picture is that if you look at this right side of the picture here, so in the center of this right side of the picture, what we have here is not a reference solution, so it's another student solution. So what happened is that there were a bunch of student solutions that when we tried to prove them equivalent to a reference solution, we got a timeout because this was very hard, they were very different. But instead, we did manage to prove them equivalent to some other student solution that was equivalent to the reference solution. And then by transitivity, we know that the solution is equivalent to the reference solution and therefore correct. So I can show you this on an example. So the reference solution is this maxm function. And one of the student solutions that would time out initially is this maxf function, for example. And you see in maxf that they're very different. Maxf uses higher order functions. It has this fold left here. And so it does stuff by comparing from left to right. The other one does from the other side. And so this induction that we tried here didn't work. So the way to make it work, we can write an intermediate solution. So this max t is more similar to maxm and maxf than they are to each other. Then we prove equivalence of the first two and the second two, and so we know that everything is equivalent. One thing that I have to say here is that writing this max t is not something that we want to do, right? This also takes some manual effort. And so we are very grateful that this algorithm can find it actually. It can use the fact that we have a bunch of solutions, and thanks to this, it can find one of those solutions among the ones that are available. Okay. Right, so far I was just telling you a bunch of stuff about how this should work, right? But to see if this actually works, let's look at some results. So here I have this table with a bunch of benchmarks, with a bunch of examples that we obtained from some tools that do similar stuff, as in they analyze student code, they do feedback, repair, and stuff like this for OCaml programs. So we took this, we translated all of those to Scala, and then we ran our tool on this and we evaluated. And I'll try to explain those numbers. So the first column, S, is the number of reference solutions that we provide per benchmark. Then P is the number of submissions, so it goes up to 800. F is the average number of functions per example. So you can see that the initial ones are one function, one program, and then it kind of grows. I also show this number of lines of code that goes up to more than 50. And at the very end, you have this most important number, which is percentage of success. So when we run our tool, how many times do we actually get an answer? So either counterexample or proof of equivalence versus timeouts. So you can see that at the start, more than 90% of for more than 90% of solutions, we did manage to classify them. And then for some of them, it was more tricky. For some examples where there were multiple functions and the students were implementing them in a way that is very, very different from what we would expect. Right. So we are getting closer and closer to the end of this talk. I kind of lied to you when I showed you the initial picture with those 3 pieces, because there are actually many more pieces in the story. They don't all quite fit the slide, right, in the talk. But I would like to list them here and maybe to tell you just a tiny bit about them. And then if you want to hear more, you can ask more. So about counterexamples, I already mentioned them briefly. So Stainless as a tool, as a verifier for Scala, has this very nice feature, which is that when it doesn't prove something or when it manages to disprove something, then it gives you a counterexample. And here in the context of grading, this is very useful because this way our tool doesn't only give a binary answer whether the solution is correct or not, but only gives you some feedback. So you see this counterexample, and that way you can fix your code. We use it even more than this, so it's not just an output, but as I told you, we use it to match potentially equivalent function calls, and we also use it to quickly disprove equivalence. So before we do the algorithm that I showed you, we run each pair on counterexamples that we discover in this search from other failed programs, right? And if we manage to disprove them, then we don't even need to do verification. That's very nice. Right, and then about this conditional equivalence. So what might happen is that you want to check equivalence of 2 programs, but disregard some input. So let's say you want to check whether a list is sorted, but only if it's not empty. And if it's empty, then you don't care. So we also have ways to deal with this. One simple way is something that you might be familiar with if you are familiar with verification, and those are preconditions. So you can put require, right, and then disregard them. And we also have other more general ways to deal with this. Then I didn't talk much about termination, and this is also very important. If you remember the slide when I defined equivalence, I said that in order for functions to be equivalent, they need to be terminating. And so Stainless as a tool also has support for automated termination checking, which is very handy for this reason, right? Because we obviously want to check this as well. In terms of performance, I didn't say anything. The pretty picture that you saw, the pretty graph with all the dots and lines, this is something that we get, as I said, by comparing many programs to each other. So against a reference program, but then also against student solutions, right, to find those intermediate solutions. And it's pretty challenging to do this without comparing each program to each other program. We don't want to compare each program to each other program because this takes a lot of time. So what we do instead is something more smart. So we have some way of defining priorities and then only checking for the top possible guesses and not all of them. I said we don't look at side effects. So what about exceptions? There were many programs with exceptions in this set of benchmarks that I showed you. So in this table that I showed you, the way we deal with them so far is by translating them to some default behavior. But long term, we are also looking into something more serious there. And then the title was Functional Programming Beyond. I only showed you at least examples of functional programming exercises, but I should tell you that Stainless as a tool also allows programs that are not purely functional, so it can also reason about loops and variables and stuff like this. Especially recently, there's been a lot of progress there. And so I can just quickly tell you that loops are simply translated into functions. So from there on, it's all easy, but there are other stuff to think about there. Right. Now it's pretty much way past my bedtime, so I would like to use this last few minutes to tell you a bit about the future. So on one side, I have this last picture that you saw, so I have this toy. On the other side, I have this first picture that you saw today, so I have this classroom. And right now, there is a bit of space in between. I'm not sure if you can see. So plans for futures are to narrow down to try to raise this space. And we are working actively these days to make this happen and to bring this toy closer to the classroom, right? To get there, your help is very, very welcome. So one way to help is if you have platforms or if you know of platforms that have Scala examples with a bunch of solutions, you can share them. I would be happy to evaluate the tool to make it better by evaluating it on those examples. And even better, you can actually go to this website. You can install the tool and try it yourself, play with some examples, and share your feedback. Yeah, that's all I have for today. And if you have questions, now is the time.
Hi, thank you so much for your talk. We have a question for you, and I'd love to get it up on screen. Just give me 1 second here to do that for you. And we will kick off some Q&A. What are the types of student programs for which this way of verification works poorly?
Right, nice. It's true. I did mostly talk about examples where everything works and everything is nice. The kinds of programs where this would not work would be, if I can go back here. You don't see slides, it doesn't matter. So if you remember from the very bottom of the table that I showed you, there were some examples with the low percentage, so such as this lambda example. So this works poorly here because the student solutions to this exercise, so the exercise is about checking whether some formulas are valid or not. And you can see here that it has up to around 2 to 3 functions per solution. And so those functions can be implemented in very various ways. So the thing is, many students would introduce helper functions that were not really planned, let's say, from the exercise. So it would implement some operations that the reference solution would not even think about. So what happens is that you have some functions that do some stuff that none of the functions from the reference solutions do. So you can never match them, you can never prove them equivalent, and so you can never prove the actual program.
That's pretty interesting, and what a great question. I think it really ties together what you were talking about and a little bit more. We have another question here, and it is, were there any examples which were way away from the expected solution? They were still correct, but were marked as incorrect and were challenged by the students.
They were correct, but marked as incorrect. Okay, so maybe this part I didn't explain very well. The good thing about this approach is that you can never have, by using formal verification, you can never have the case where you claim that something is incorrect even though it's correct. So you always get, if stuff is incorrect, you always get a counterexample. If it's correct, you always get a proof, right? So no, we didn't have cases where solutions were correct, but the tool would say that they are incorrect. The way this can happen in general, in like maybe using other similar approaches or stuff like this, is that you might have a test case that shouldn't be allowed. So what I said about checking whether a list is sorted, and only for non-empty lists. It could be that in your test cases, you mistakenly add a test case, which is an empty list. And then for this empty list, the student didn't solve it at all, or didn't solve it the same as you would solve it, but it doesn't matter, right? Because you say for a non-empty list. So let's say that this would be another flow of testing. But in this case, in our approach, this should not happen.
Well, thank you. Thanks for re-clarifying that too. That is all the questions we have right now. But Dragana, thank you so much for being here with us. And I hope you get to enjoy the rest of the conference that's going to kick off tomorrow. And have a wonderful evening. We'll see you soon.
You too, bye.
Fire in retro rock.
Roger, Matt. Ready to eject.